Hello and welcome back to the lab. Today on the bench we have two pieces of gear that I use pretty regularly in the lab. We have a Heathkit IT28 and we have a Keithley 2450 source measure unit. These are on the bench today because I got some capacitor questions. I've been getting a lot of capacitor questions about how some of these works and some of the readings I've been getting and some of the testing methodology and things like that that I've used. So I've got a couple of the units. We'll grab a couple capacitors and I'll see if I can't shed some light on what's going on somewhat behind the camera and behind the scenes. So I would probably assume most people who are viewers of this channel have at least seen one of the Heathkit capacitor testers before, or the old eye style capacitor bridge and leakage testers. So this has a capacitance bridge in it. This is not calibrated. I need to get some standards so I could actually calibrate the bridge. But the leakage is in good shape. However, there's a problem with it that I will demonstrate in this video. And it has to do with unregulated power supplies. Over here is a source measure unit. This is a more exotic piece of test gear. The best way to describe this unit is this is a high stability, high accuracy power supply, a 6.5 digit DMM, and an ideal current source all rolled into one. And it's also a 4-quadrant measurement, which means I can have it source a negative voltage and supply a positive current, or source a negative voltage and a negative current. So where a power supply can only source a voltage and source a positive or negative voltage and a positive current, this can actually sync current, source voltage, positive and negative, which makes it a full 4-quadrant device. So, and the other thing that's really unique about source measure units is they can sweep the current. So I can start at a negative voltage and a positive current, and I could sweep all the way up to a positive voltage and a positive current. And I can also do it in any of the 4 quadrants that I want. So ideally, this makes it a good 2-pin curve tracer. There's even a curve tracer app for this, for 2-pole measurements and 2-pole with 4-wire measurements. Now this wouldn't do a 3-pin device like a transistor or anything like that, because it doesn't have base drive. That's where my other 576, 577s come into play. And also I'm hoping to get a few more of these, because I need to measure some tubes, and I have another video coming. I've been getting the question a lot of, why can't you just use a curve tracer to match some tubes? And the answer to that is you can, but it's complicated and limited. But we'll get into that in a different video. We're going to use some of the extremely low measurement capabilities of this source measure unit today. This particular unit can read in the tens of femtoamps. Now, I don't have guard voltages and things like that set up, so I can't get down that low with just long leads. When you're talking about counting electrons quite literally, everything starts to matter. How long the leads are, where the unit is, what you're measuring, guarding, noise, all kinds of stuff. It gets way into the weeds pretty quick. But we don't need that for capacitor testing and things like that, which is what we're trying to do today. So essentially, this particular unit can read currents, and it can also source currents very precisely. And I can, as long as I stay under 100 milliamps, I can go up to 200 volts on this unit. One of the other ones that I want to add to the lab, especially for doing some tube testing, is I would like to add a 2750, if I remember the number right, and I'd also like to add a 2651. The 2651 is exactly the same unit, looks identical. It's the high current version, still tops out about 200 volts. But it can do 200 volts at 6 amps. The 2750 is the high voltage version. It stays at 100 milliamps, but it can do 1,000 volts. So it'll be, and because it can source 100 milliamps at 1,000 volts, we'll be able to really measure some tubes very precisely, which is kind of why I want to do it this way. But that's future plans and things like that. So to measure capacitors, well, let's talk about how this thing measures first, and then we'll get into how I can use this to somewhat replace the job of this and also some of the problems. So on the IT28, when you do a leakage test, you use these two banana plugs right here, and you tell it what voltage you want to source, 3 to, 600 volts, and this way. And then you tell it whether you have an electrolytic, a mini-lytic, or a paper or mica capacitor, etc. Now, this is a vacuum tube-based unit, so it can go to high voltage, and it has high voltage in it, which is why a lot of people like them, because you can test capacitors at rated voltage. The problem is, if I have this knob all the way up, like that, and I do this, there's 600 volts across that terminal right there. Doesn't matter what position this switch is in, doesn't matter anything else, there's 600 volts right there. Actually, more than that, which is why I'm going to get into a problem with this thing in a minute. So you have to be really careful, especially if you put a large capacitor right there. Now you've got 600 volts with a charged capacitor at 600 volts. Stuff's starting to get spicy. So always bring this back down and leave it in the discharge mode. Bridge is when this is functioning up here. But because I have some other units to test capacitors, I don't use the bridge function on this a lot. A lot of guys like to try to reform capacitors. You will note that I don't do that in the channel. The jury's out on if that does or does not do anything. But a lot of guys like this unit because this is not spring-loaded. Like on the Sencor units, you have to hold this to put the voltage at the test terminals. So because of that, you can leave this here and you can leave this on for weeks, days, months, if you're doing that kind of thing, and go from there. I don't particularly do that because of some chemistry in the capacitors. I would rather replace it with if I want to be in the unit one and done and have it be on the bench now for 10 to 20 years before I have to service it again. So if I have to replace, I don't mind replacing some of the components, especially if they're getting beat on. Now, some of the caps in, say, a linear power supply, they don't get beat on that much because they're running at 60, 50 hertz, depending on what your main frequencies are. A capacitor in a switch mode power supply, it's getting the living crap beat out of it. Switch mode use is very tough on capacitors. They don't live long there, and it really puts them through the ringer. So all capacitors, regardless of type, regardless of make, regardless of vintage, regardless of anything, will exhibit some leakage. They're real components. They will leak some DC through them. Everybody says they're ideal, things like that. They're not. Some will get through. Now, how good the capacitor is depends on how much of that some gets through. And that's actually the first thing we want to get into is how does this thing actually test capacitors and read them? It's current based. So when you calibrate one of these, you have the test voltage here. And all this switch is doing when you move this up and down is it's adjusting the test current. Not the charge current, that's the same. It's the leakage current. So if you have it in electrolytic, which is the worst one, if I remember the spec sheet, or if I remember the calibration document correctly, it's 25 microamps. So anything under 25 microamps will close the eye and it'll be a passing, or it'll open the eye and it'll be a passing grade. The mini lytic is 5 microamps. Will open the eye and it'll be a passing grade. And the paper and mica is 2 microamps and it'll be a passing grade. That's what you adjust the 3 resistors in here for when you're doing that. On this unit, I can set what I want the passing grade to be, and it can do pass-fail testing and things like that. I can say if it leaks higher than X, it passes, or if it leaks higher than X, it fails, or it passes. So that's all settable in the UI for the SMU. And I also have much better measurement capabilities because this only goes down to about 2 microamps. Now, we're pretty in the weeds at 2 microamps. But 2 microamps of current will pass on the most sensitive setting. I can see femtoamps of current on this unit. So it also depends on what we're measuring and things like that. Obviously, the higher voltage a capacitor is in service, the less leakage it can have, because the more leakage it has, the more it's going to self-heat, and all kinds of bad things are going to happen. Also, some things can be, this can affect timing circuits. So if the value of the capacitor needs to be fixed because it's being used in like an RC timing circuit for, say, a sweep for a scope or something like that, if it's leaking, your sweep speed will be slow, because as it's supposed to do the RC time constant and charge up, it's leaking current, so it's not charging as fast, so your sweep speed will actually be slow. So depending on the service of the capacitor, this can be hypercritical, or it could be not that big a deal. Really depends on the circuit the capacitor lives in. So one of the problems with this thing is it has an unregulated power supply. Now, what we can do, we can prove that with the fluke. And because it has an unregulated power supply and my line voltage running kind of hot, now these have been on for probably about a half an hour, so they're nice and warmed up. We have it on the 3-volt setting. We'll hit leakage, and we're at 3.7. And you'll see the eyes closed because the meter impedance isn't even enough to, the meter impedance is too much current to open the eye. But if I set it to electrolytic, the meter impedance is now enough where we have enough current, or not enough current to close the eye. Not mini-lytic. And then on the paper and mica setting, the eye's closed. That's just from the, I think this is 10 meg, 1 meg, 10 meg input impedance on the meter. So if we, say, go to 15 volts, so I'm set to 15 volts, this is 16.87. So this can be a problem when you're testing a modern day capacitor on one of these IT28s if you haven't adjusted the line voltage, because these were designed for 115 volts. I'm in North America, so we run on a 120 volt system, which my lab sometimes hits 125 because I monitor that a little bit. So some of this gear that doesn't have regulated power supplies, it'll also read higher. But as I've said in a lot of the videos, modern capacitors are not tolerant of overvoltage at all, period. Vintage capacitors are tolerant of overvoltage. This has to do with some of the chemistry in the capacitor, which is the insulating layer. Because the electrolytic is caustic, what happens is, as the capacitor sits on the shelf, the insulating layer gets thinner and thinner and thinner because the acid in the electrolyte is eating the layer. Well, what happens is when it sees voltage, a current passes through the capacitor, but it regrows that layer. So as long as the capacitor doesn't totally overheat and catastrophically fail, that layer can get thick enough where the leakage drops to an acceptable level, and the capacitor can handle a slight bit of overvoltage. This is also very important in tube circuits with the power-up spike. So before the tubes come into emission and drag the supplies down, you can see 100, 200 volts above normal operating voltages. Actually, the 412, no, the 400 CD video is a great example of that, because on the B plus side, it hits like 465 volts. So I had to put a 500 volt cap in because it wasn't. But at running, if you measured it running after the tubes were all warmed up and it was doing its thing, it was down about 350. So over time, it would burn up a 450 volt cap. I had to go to 500 volt caps to prevent power up surge from nuking the supply or nuking the capacitor. So we're at 16 volts. We'll crank it all the way up. I'm supposed to be at 600, but because of the error in line voltage, we're at 650 volts. So you try to test a 600 volt modern cap there, absolutely this is going to do some damage to that capacitor. It's going to overheat it and cause it to draw heavy current and make it not have a good day. So just something to be aware of. This can be adjusted with a variac, bring it down a little bit or not. I usually end up, because I know this, let's say it's a 150 volt capacitor, I'll use the 100 volt setting just so I don't have that voltage error in there, and I'll kick it up. I could probably change some of the resistors in this divider and get a little closer, but it's working, and it sees use. But now that I have the SMU, I tend to use the SMU a little bit more than I use that nowadays. So let's test a cap and see what happens. So let's see. This is a 2500 microfarad at 75 volts DC. So if I set it to 50, we're at 53 volts. That'll be safe for the cap. So we'll turn this off the discharge so we don't get shocked. And then I'm going to hook the capacitor up to the tester, and then I'm going to hook the meter up to the capacitor, and we can see what's going on. Okay, so I have the capacitor hooked up, checking polarity, and we'll turn it to the electrolytic because this is an electrolytic. But what we're going to see is I have it on the 50 volts, 75 volt cap, and we'll set it to leakage and watch the meter. See how slow it's charging? So now we'll notice the eye's closed. So what will happen is this is current limited, so it's going to take it a while to charge. This is also a very large cap to be testing on this unit, so this may even not test. But because the charge current is so low, we're watching the RC charge curve right now because this is a very high impedance, low current source. But if this kind of plateaus and stops, that's where we're going to see the leakage. So the cap is still failing testing, the eye's still closed, and we'll see if this slows down. And we're starting to slow down a little bit. So, at least from a testing standpoint, this cap is not testing very well. Yep, and there we go. We've kind of plateaued, as we can see. And we did see that the meter impedance, so we are losing a little bit of current over the meter impedance. I'll have to give it that. But we did see that on the electrolytic setting, it would open up the capacitor, or it would open up the eye on the with the DMM hooked up. So that can't be the problem. Our extra resistance and leakage has to be the capacitor itself. So it's going to get there, but it is definitely slowing down. Now, when people talk about reforming capacitors and things like that, we're actually watching the reformation process happen on the meter. This could take a substantially long period of time. It can run, and then it'll as long as the cap doesn't blow up, it might make it to rated voltage. It might not. Now, also remember, the current of the IT28 is not set by the voltage. It's set by the... so if I kick this to 100, it's not going to go much faster than this. But this is a 75 volt cap, and it's struggling at 45 volts. So it's not looking too hot. I have an exact other capacitor. Let's do the exact same testing on the SMU. And I won't even, just to keep it fair, I won't get rid of the meter, so we have the meter's impedance over the SMU. We'll set the SMU to 100 milliamps, and we'll fire 75 volts in this and watch what happens. Oh, for safety's sake, discharge. Now we're going to watch the voltage fall. Now, the other thing that's really nice about that the IT28 is when you discharge, it doesn't explosively discharge the capacitor. It slowly brings it down through a resistor, which is important because dumping all that charge that quickly is not, can be hard on the cap if they're not made for that. But once I unplug this, there's something else I want to talk about because it was soaking. We had a bit of dielectric absorption. So when I take the leads off, we'll let it come all the way down. When I take the leads off, we'll watch the voltage start climbing back up on the capacitor with it not hooked up to anything. I'm just going to wait for the eye to open. And I'm doing this in real time too, so feel free to skip ahead. Wow, it's pretty slow to discharge. Actually, turn this back down. Not that that's going to do anything to the discharge rate. Okay, the eye's open, and we're at 1.6 volts. I'll unplug this now. And immediately it started going back up. So this is dielectric absorption. In this particular capacitor, it's probably not going to be that huge a deal. This is 1.6 volts, might get up to 10, 15-ish volts. I mean, that's enough to maybe buzz somebody. In much larger capacitors, also high voltage capacitors, 1.5 kilovolts, 300 volts, 400 volts, 500 volts. This becomes a much more significant safety problem because the caps can recover a substantial amount of their charge after the unit's been off for a couple of hours. So something to be aware of and know that it is going on. Okay, I've got the capacitor hooked up to the Fluke DMM again, and we're going to reset the timer on this because this will shut itself off. One of the reasons why I like bench DMMs is they don't turn off on me. We'll go to menu, source measure. We want to source voltage and measure current. So we're going to put 75 volts across these two pins. And so let's do 70 volts. And then we're going to do, can I do 100 milliamps? Will it let me? Yes, it does. It will let me. So I've set the source. I've told the SMU that I want 70 volts, and I've told the SMU to source out 100 milliamps into the capacitor. So we shouldn't be current limited in. We should not be current limited coming out of the SMU. So what we should see is we should see the voltage rise to 70 volts, and then we should just see the leakage current in the capacitor and what it's doing. So this is what I'm doing when I was saying I'm seeing X number of milliamps through the capacitor. So I'll turn the output on. And we're already at current limit, and the voltage is climbing. And for 100 milliamps of current, it's stalling out pretty quick. 46, 45, and actually the voltage is dropping across the capacitor. So we are leaking through this capacitor at 45 volts, 100 milliamps of current. This is not a good capacitor. It's actually kind of cranky. No, nothing shorted and anything like that. So this cap won't even make it to... Yeah, and the current's actually falling. Actually, let me source current and measure voltage. And we'll set this at 70 volts. And we will do 100 milliamps again. Fire this back on. And now we're doing the same thing. I just flipped the parameters. So instead of sourcing voltage, I'm sourcing current. So I'm dumping 100 milliamps into the capacitor. And I said, as long as I'm dumping 100 milliamps into the capacitor, you can go up to 70 volts to continue dumping 100 milliamps into the capacitor. So this capacitor is passing 100 milliamps of current, which means, actually, let's do that. Measure source current and measure resistance. So because this capacitor is passing 100 milliamps of current, this capacitor is a 423 ohm resistor, 4.22, 0.422K. So that's not a capacitor anymore. That's a resistor, at least according to the Keithley. And see, we've stabilized at 42 volts. And we're even falling, so the resistance is getting worse, not better. Now, if I put this behind a rectifier, right? So I have a full bridge rectifier that takes AC mains, jumps it to DC, and dumps it into this capacitor. I'm dumping mains current into a 400 ohm resistor. There's a lot of current there, so this will blow a power supply. Absolutely no question. It'll toast it. So that cap is not good. And look at the voltage fall after I turn the output off. This is just through the meter impedance. So this is just through the input on the DMM. The error was just saying because the source was off, it couldn't measure, which is fine. So we're at 26 volts. Let's crash this out. I don't want to short this out, even though it's a bad cap. There's probably a decent amount of juice still in there. Okay, well, I have that discharging off to the side. Let's prove out the testing methodology. So we'll hook this up to the SMU, and I have the DMM hooked up to the SMU. And we're going to ask for the same 100 milliamps of current, but then we have a voltage limit at 70 volts, so I'm not going to change anything. We'll see what the resistance says of the input of the multimeter. Bang! And done. We ended up volt limiting out. I'm sure there's, 70 volts exactly across the meter. And we're reading 9.0 megohms of resistance in the DMM. So we know the SMU and the testing methodology is working. So definitely problems. Let's see what a good cap looks like. Okay, I have a very high quality capacitor hooked up to the input of the SMU. And we're just going to go for broke on this one. I've got 100 milliamps of current, and I want you to give me a full 200 volts. This cap is rated for 400 volts, so this won't be a problem. And this is a non-polar cap, so it doesn't matter which way it goes. Although the band end is marked, I do test all those on my capacitors. But let's see what the leakage current is across this capacitor. And what we'll do is we'll do this. We'll source voltage and measure current. And I'm at 200 volts. And, or no, I'm sorry. We will source current and measure voltage. So we're sourcing current through the capacitor, measuring the voltage. If it maxes out, if it limits out at 200 volts, we'll see what the current is across this capacitor at 200 volts. All right, that didn't work because we never got to 100 milliamps. So let's source voltage and measure current. And, oh yeah. 200, okay. Limit is 10 microamp. There it goes. I wasn't reading the interlock properly because I went up to 200 volts. So let's slow this down a bit. Number of power line cycles 15. Oh, yeah, got to go to 10. It's not that, it's not like with the meters. 10. And we do want to filter so we get accurate. Measurements are going to be a lot slower now, but we'll get good measurements. So with a very good capacitor, we are reading 1.25 nanoamp. Way more sensitive than the microamps on that guy. And this is actually running now at 700 picoamps. (100 picoamps). So it's going to bounce around a lot. It's not. It's noise. If I really wanted to measure down here, I need guarding, Faraday cage, things like that. There's a lot of things I need to do to tighten this measurement up. But the fact that we're measuring picoamps, especially with leads this long, and a few other things on this capacitor, it is a very, very good capacitor. And we're just dropping it so you could see it was filled up. I'm just using the meter impedance to discharge the cap because I didn't want to touch a 200 volt cap because it was fully charged. Okay, I have hooked up a 68 microfarad 350 volt high quality electrolytic capacitor just so we can see that the electrolytics are a little worse. That was a poly cap and it was a very good capacitor. I'm going to keep it at 200 volts because I can take 350. And that will be fine. So I've added it to the 10 milliamp source current. And let's turn on the output. And set this back down to 1. No filter. And we are drawing now we're charging. I did that backwards. Well, that's wrong. I was wondering why the numbers were so low. I just reverse biased that capacitor and oops. Well, he about smoked out. I was wondering why that was looking very strange. And it's because I got the leads reversed. Oh, well, good news is I didn't hurt the SMU, but I definitely did hurt that capacitor, so let me get another one. Oh, yeah, that's warm. That's not good. Double checking. Force high is to the plus, force low is to the minus, and we now have a 22 microfarad 400 volt capacitor. So we'll do this again. Source voltage and measure current. 100 milliamps, 200 volts. And there we go. Now this is going to come down quite a bit, so we're in nanoamps already because we're 0.0 milliamp. But if we watch, this is behaving correctly. If we go to resistance, We'll see the resistance of the capacitor climb. It's already so we're at 3 megohms now. And it's going to continue to climb as it sees voltage. We'll get to 4 megohm. And if we go back to source voltage measured current, we're into the tens of microamps. This will continue to drop as the capacitor soaks. One of the things Marco Reps did in one of his videos when he needed a very high value, low leakage capacitor, he let these things soak overnight. This is partially dielectric absorption. This is partially the shoring up of the insulating layer and a few other things that are happening to the capacitor. But this could very easily get into the nanoamps, and the stuff that he let soak overnight got into, I think it was like 6 nanoamps or something like that for an electrolytic. So as they see voltage, they'll get even better and better and better. Microamps is fine. Remember, microamps will trip the 25 microamps will open the eye on the IT28. We're almost at 25 microamps. So all capacitors do have some leakage, even the really good ones, but tens and hundreds of milliamps of leakage is not what we're looking for. Also, if you look back in the video when I had this capacitor wired backwards, with it reverse bias like that, when the resistance went nuts, that's why these cascade and they blow up. If this wasn't current limited and it was a just a rectifier or something like that, this would have very easily overheated and gotten really cranky and popped its top, vented all the electrolyte, and made a big mess in the lab. So that's why electrolytic capacitors have a polarity, unless they're the weirdo non-polarized electrolytic caps that I keep running into in random audio gear, which is fine. I'm going to let this soak for a while. Just through the magic of the camera, you guys won't have to wait at all. But I'm going to leave this run, let it soak, and I just want to see how low this is going to get. Not going to let it soak overnight or anything like that, but for an hour or two, while I do some other stuff around the lab. All right, I am pretty sure we will ultimately get under microamps because we're at 6 microamps now, and it's still falling. Where are we at for resistance? Source 30 megohms. So we're getting up there. Slow this down so we get better measurements. Nope, not relative. Filter. So we're still climbing in the megohms. So the cap's getting better and better and better as it sees voltage. So it'll continue to do that for a while yet. Here we are on the voltage and current scale with the 10 power line cycles and the filtering. 6.2 microamps. This will continue to go down probably. Yeah, 183. It'll go down some more. 169. So yeah, it's continuing to go as it's going. So the longer it sits here and soaks, the better it's going to get. But it would probably get into the nanoamps, maybe even to the bottom of the nanoamps if I gave it enough time. But that should be good for demonstration purposes. We're going to discharge this through the DMM and make that cap safe to handle again. Actually, probably do it through. Actually, let's just move it over. We'll just pull this up. Pop this in the IT28. Let it discharge. And looks like it's already discharged, so cool. The IT28, if we did, what was this cap? A 400 volt. So if we do 350, and we're on the, actually let's do the paper and mica, the low, nah, because it's not under 5 microamps yet. So the mini lytic leakage. Here's another interesting effect with capacitors is they kind of get used to the voltages they're run at. So this was running at 200 volts. So if we hit this at 300 volts, we'll see it go to 200 real fast, but now it's going to climb for a little bit for 300. And there's the eyes open. Up, it's closing and opening again. Some of that's the meter's influence for being in circuit. There it goes, 363. So they'll get used to the voltages they're sitting at, so they'll have really good characteristics there, but if they see more voltage, it'll take them a while to get used to that higher voltage. So this really doesn't have any bearing other than extreme voltage circuits. But now that we've had voltage on it, let's check the dielectric absorption. It's now unplugged from the IT28. And as with the other capacitor, we're watching the voltage climb back up. This could very easily hit 25 volts or so before it kind of settles back off. So just another thing to be aware of. Well, thanks for stopping by the lab and taking a look at this capacitor video. I hope this demystified some of the stuff that's going on in the background and answered a couple of questions that I've been getting. If you guys have more questions, leave me questions in the comments below. I read all the comments on all the videos. As always, more is on the way, and I will see everybody in the next video. Bye for now.